wave speed on a stretched string. In this lesson, we need to determine the factors that affect the speed of a wave on a string, and to write a mathematical expression for the speed of a wave on a string. Wave travels through a medium such as water, air, steel, or a stretched string. The wave requires kinetic energy and potential energy to cause the particles of that medium to oscillate. So, the mass refers to the kinetic energy and elasticity refers to the potential energy of the string. Thus, the mass and elasticity determine how fast the wave can travel. Here, we find that dependency by making dimensional analysis and derivation from Newton's second law. In making dimensional analysis, we carefully examine the dimension of all the physical quantities that enter into a given situation to determine the quantities that they produce. In this case, first, we examine the mass and elasticity to find a speed, which has the dimension of length divided by time. Second, mass. We use the mass of a string element, which is the mass of the string divided by the length of the string. Third, ratio. We call this ratio the linear density of the string. Thus, mu is equal to m over L. To see how the speed of a wave on a string depends on the tension and the linear density, consider a pulse sent down a taut string. The string has been stretched and pulled taut by forces as its two ends. The tension T in the string is equal to the common magnitude of those two forces. As a wave travels along the string, it displaces elements of the string by causing additional stretching, with adjacent sections of string pulling on each other because of the tension. Thus, we can associate the tension in the string with the stretching of the string. The tension and the stretching forces it produces have the dimension of a force, namely ml over t squared, that come from F equal to ma. We need to combine mu and the force to get the dimension of L over t, which is the velocity. A little juggling of various combinations suggests V equal to c square root force over mu. The speed of a wave depends on the properties of the medium in which it travels. The speed of a transverse wave on a stretched string or cord, for example, depends on the tension in the cord, Ft, and on the mass per unit length of the cord, mu. If m is the mass of a length, L of wire, mu is equal to m over L. For a wave of small amplitude, the wave speed is described as v equal to square root ft over mu. This formula makes sense qualitatively on the basis of Newtonian mechanics. That is, we do expect the tension to be in the numerator and the mass per unit length in the denominator. Why? Because when the tension is greater, we expect the speed to be greater since each segment of cord is in tighter contact with its neighbor. Also, the greater the mass per unit length, the more inertia the cord has and the more slowly the wave would be expected to propagate.